It happened at 4:45 a.m. U.S. Central Daylight Time. On September 14th, 2015, two machines, one in Livingston, Louisiana, and another 3,002 kilometers away in Hanford, Washington, felt a tremor. It was not a tremor in the Earth. It was a tremor in reality itself. The Laser Interferometer Gravitational Wave Observatory, or LIGO, had been built for this moment. For decades, scientists had theorized about ripples in spacetime. They called them gravitational waves, but they had never seen one. Not directly. The signal was tiny. It distorted the 4-kilometer long arms of the detectors by less than 1/10,000th the width of a proton. But it was unmistakable. The computers flagged it immediately. The signal, a gentle chirp that rose in frequency over a fraction of a second, was the sound of a catastrophe on a cosmic scale. It was the sound of two black holes colliding. The analysis took months to confirm. The data was breathtaking. About 1.3 billion years ago, when life on Earth was just beginning to form multicellular organisms, two black holes were circling each other in a distant galaxy. One was 29 times the mass of our sun, the other was 36 times the mass of our sun. They spiraled closer and closer, whipping around each other at nearly the speed of light. In the final moments, they merged. In that instant, they converted 3 times the mass of the sun directly into energy. Not as light, not as heat, but as a violent, expanding wave of pure gravitational energy. A storm in the fabric of space-time. This wave traveled across the universe for 1.3 billion years. It passed through galaxies, stars, and nebulae without leaving a trace. It was a ghost. Then, on September 14th, 2015, it washed over Earth. It stretched and squeezed everything it touched. It stretched and squeezed the LIGO detectors, and we saw it. For the first time, humanity had directly witnessed space-time bending, warping, and ringing like a bell. It was a new way to see the universe. It was proof that the most violent events in the cosmos are not just explosions in space. They are explosions of space. Number 21. The beginning was a point. Before the universe, there was no space. There was no time. All the energy and matter that now make up hundreds of billions of galaxies was compressed into a region smaller than a single atom. This point had infinite density and infinite temperature. This is the Big Bang singularity. The laws of physics as we know them do not apply there. The speed of light during the universe's first 10 raised to the power of 43 seconds was likely not constant. The 4 fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were all unified into a single superforce. This concept comes directly from Albert Einstein's theory of general relativity. If you run the clock of the expanding universe backward, all the galaxies rush together. The math leads to a single point in the finite past. This idea was first proposed not by a physicist in a lab, but by a Belgian Catholic priest and astronomer named Georges Lemaitre in 1927. He called it the hypothesis of the primeval atom, or the cosmic egg. He based it on the equations of relativity years before Edwin Hubble provided the observational evidence that galaxies were indeed moving away from us. The singularity itself is a problem. It's a point where the math breaks down. The equations produce infinities, which tells physicists that the theory is incomplete. General relativity is a brilliant description of gravity on large scales, but it doesn't include the rules of the very small, which are governed by quantum mechanics. To understand the singularity, we would need a theory of quantum gravity, a theory that unifies these two pillars of modern physics. We don't have one yet. What happened right after the singularity is almost as strange. In 1980, physicist Alan Guth proposed the theory of cosmic inflation. In the first tiny fraction of a second, from about 10 raised to the power of 36 to 10 raised to the power of 32 seconds after the Big Bang, the universe underwent a period of explosive exponential expansion. It grew from the size of a proton to the size of a grapefruit almost instantly. This rapid stretching smoothed out any wrinkles or irregularities in spacetime, explaining why the universe today is so remarkably uniform and flat on large scales. This inflation was a warping of spacetime on an unimaginable scale, setting the stage for everything that came after. It was driven by a type of energy called the inflaton field, which has since decayed, but its effects are imprinted on the cosmos. The singularity isn't a place in space. It's the moment that space and time began. Number 20, the hologram you live in. The maximum amount of information that can fit into a region of space is not proportional to its volume, but to its surface area. The information to describe a three-dimensional object, like you, could be entirely encoded on a two-dimensional surface. The universe you perceive as three-dimensional might be a projection, a hologram, of information stored on a distant 2D boundary. This is the holographic principle. This idea didn't come from science fiction. It emerged from the study of black holes, specifically the work of Jacob Bekenstein and Stephen Hawking in the 1970s. They discovered something strange about black hole entropy, which is a measure of disorder or information. They found that the entropy of a black hole isn't proportional to its volume, as you might expect. It's proportional to the surface area of its event horizon, the boundary of no return. It's as if all the information about everything that ever fell into the black hole is smeared out and stored on its surface. In 1993, physicist Gerard Hooft took this idea a step further. He proposed that if the information for a 3D object, like a black hole, can be stored on its 2D surface, then perhaps the same is true for the entire universe. The universe itself might be a hologram. Juan Maldacena later provided a concrete mathematical model for this, known as the ADS-CFT correspondence, which connects a theory of gravity in a certain kind of five-dimensional spacetime to a quantum field theory without gravity on its four-dimensional boundary. This correspondence has become one of the most powerful tools in theoretical physics. Experimental tests for this are incredibly difficult. At the Fermi National Accelerator Laboratory, an experiment called the holometer was built to look for evidence. The idea was that if our 3D space is a projection, it might be pixelated at the smallest possible scales, the Planck length about 1.6 x 10 raised to the power of 35 meters. This would create a fundamental jitter or uncertainty in the position of things. The holometer used powerful lasers to try to detect this background noise in spacetime itself. After running from 2014 to 2016, the experiment found no such jitter, ruling out some of the simpler holographic models. But the principle itself remains a powerful and deeply strange idea. It suggests that the fabric of spacetime might be an emergent property, a kind of illusion generated by quantum information living on a lower dimensional surface. The world is not what it seems. Number 19, when the rules of physics change. The vacuum of space is not empty. It is filled with quantum fields and has a certain baseline energy level. This is the vacuum state, but this state might not be the true lowest energy state possible. Our universe could be in a false vacuum, a metastable state, like a ball resting in a small dip on the side of a large hill. It's stable for now, but a sufficient jolt could send it rolling down to the true vacuum, the lowest point on the hill. A false vacuum decay would be the ultimate disaster. If this happened, a bubble of the true vacuum would spontaneously appear somewhere in the universe. Inside this bubble, the fundamental constants of nature would be different. The masses of elementary particles, the strength of forces, the very rules of chemistry and physics could change. This bubble would expand outward in all directions at the speed of light. You would not see it coming. One moment, everything is normal. The next, you and everything around you are converted into a new form of matter governed by new laws, likely releasing an enormous amount of energy in the process. This isn't just about destroying a planet or a star. It's about rewriting the source code of reality itself. The transition would be absolute. The idea of vacuum decay comes from our understanding of the Higgs field, the field that gives elementary particles their mass. The current measured mass of the Higgs boson and the top quark suggests that our universe's vacuum is very close to the line between being perfectly stable and being metastable. Some calculations suggest it is indeed metastable with a lifespan that is incredibly long, far longer than the current age of the universe. The probability of a decay event happening in our observable universe anytime soon is fantastically small, but it's not zero. This concept introduces a profound sense of cosmic fragility. It suggests that the stability of our entire existence depends on a quantum field remaining in its current configuration. We live in a particular phase of spacetime, just as water can exist as ice, liquid, or steam. A phase transition to a different kind of spacetime would not be an explosion in space. It would be the end of space as we know it, replaced by something utterly alien. Number 18, hiding in another dimension. Our universe, with its 3 dimensions of space and 1 of time, might be just a slice, a brain, floating within a higher dimensional space called the bulk. Gravity is unique among the forces. It is incredibly weak. The electromagnetic force holding a tiny magnet to a refrigerator door is vastly stronger than the gravitational pull of the entire Earth. Brain world theory offers an explanation. Perhaps gravity is not actually weak. Perhaps it just seems weak to us because most of its strength is leaking out into these extra dimensions. This idea is a cornerstone of some versions of string theory. String theory requires extra spatial dimensions for its mathematics to be consistent, typically 10 or 11 dimensions in total. For years, the assumption was that these extra dimensions were curled up into tiny subatomic shapes, too small for us to ever perceive. But in the late 1990s, physicists Lisa Randall and Raman Sundram proposed a different idea. They suggested that an extra dimension could be infinitely large. In their model, our universe is a 3D brain where all the particles and forces of the standard model electromagnetism, the nuclear forces, are trapped. We can't move or see into the extra dimension, but gravity is different. Gravity is a property of space-time itself, so gravitons, the hypothetical particles that carry gravity, are not stuck to the brain. They can travel freely through the bulk. This dilutes the force of gravity, making it appear weak in our 3D world. This has testable consequences. If this model is correct, it might be possible to create microscopic black holes at particle accelerators like the Large Hadron Collider LHC. Normally, creating a black hole requires crushing matter to an impossible density. But if gravity gets much stronger at very short distances because it isn't leaking into the bulk as much, the energy required to form a tiny black hole would be much lower, potentially within the reach of the LHC. These mini black holes would be harmless, evaporating almost instantly through Hawking radiation. So far, no such events have been detected, which places constraints on these theories. But the possibility remains that our entire reality is just a membrane in a much larger, higher dimensional cosmos, and space-time itself has a geometry we can't fully perceive. Number 17, the froth at the bottom of reality. At the smallest possible scale, space and time lose their smooth, continuous nature. The fabric of space-time is not like a placid sheet of glass. It is a chaotic, bubbling, turbulent sea of quantum fluctuation. This is the concept of quantum foam, or space-time foam. It was first proposed by physicist John Wheeler in 1955. He realized that the Heisenberg uncertainty principle, a cornerstone of quantum mechanics, should apply to space-time itself. The uncertainty principle states that you cannot simultaneously know certain pairs of properties, like a particle's position and momentum, with perfect accuracy. This principle, when combined with general relativity, implies that at extremely small scales, the geometry of space-time must be constantly fluctuating. Tiny wormholes and baby universes could be popping into and out of existence in a fraction of a second. The scale at which this happens is the Planck length, about 10 raised to the power of 35 meters, and the Planck time, about 10 raised to the power of 43 seconds. These scales are so small that they are far beyond our ability to observe directly. This foaminess would have real effects. A photon traveling across billions of light years of space would have to navigate this choppy sea. The cumulative effect of these tiny fluctuations could ever so slightly alter the photon's path or speed, depending on its energy. Or high energy gamma rays should be affected more than lower energy radio waves. We can look for this effect. Astronomical observations of distant gamma-ray bursts have been used to test this idea. If spacetime is foamy, high-energy photons from a burst should arrive slightly later than low-energy photons, even if they were all emitted at the same instant. Observations from NASA's Fermi Gamma Ray Space Telescope have looked for this time delay. So far, the results have been negative. Photons of different energies from distant bursts seem to arrive at the same time, suggesting that if space-time foam exists, its effects are much smaller than what some models predicted. This doesn't rule out the idea, but it does constrain it. It tells us that space-time is remarkably smooth, even down to scales far smaller than an atomic nucleus. But the fundamental idea that the fabric of reality is not static, but a dynamic and chaotic quantum entity remains a driving force in the search for a theory of quantum gravity. Number 16, the Great Cosmic Rebound. The universe began with a Big Bang, and it is currently expanding, but what if this isn't the first time? The Big Bounce is a cosmological model that suggests our universe is part of an endless cycle of expansion and contraction. The Big Bang was not a beginning, but a transition from a previous collapsing universe. Space-time did not come from a singularity of infinite density. Instead, it contracted to a very small but finite size and then bounced back, starting a new phase of expansion. This idea avoids the singularity problem of the standard Big Bang model. In a bouncing universe, the laws of physics never break down because density and temperature never become infinite. The bounce itself would be governed by the principles of quantum gravity. As the universe contracts, quantum effects that are normally negligible on large scales become dominant, creating a repulsive pressure that halts the collapse and forces space-time to expand again. One of the leading modern versions of this is called loop quantum cosmology, LQC. LQC is an application of loop quantum gravity, a candidate for a theory of quantum gravity. In LQC, spacetime is not continuous. It's made of discrete, indivisible atoms of space. There is a minimum possible volume. You cannot squeeze space down to a point. As the universe collapses, it reaches this minimum size, and then the quantum nature of spacetime itself forces it to rebound. This cyclical model has profound implications. It suggests that time has no beginning and no end. Our universe could be just one in an infinite series of universes. Information from the previous universe could have even leaked through the bounce, potentially leaving a faint imprint on our cosmic microwave background radiation, the leftover heat from the Big Bang. Scientists are actively searching for such signatures. The Big Bounce changes the story of our origin. Instead of a singular creation event, the cosmos is a timeless, oscillating entity, forever dying and being reborn. Space-time itself is recycled. Number 15, the ultimate cosmic tear. The expansion of the universe is accelerating. An unknown force, which we call dark energy, is pushing space-time apart. But what if this acceleration doesn't stay constant? What if it increases? This leads to a terrifying, speculative end of the universe scenario called the Big Rip. In this scenario, the expansion of space-time becomes so powerful that it overcomes all other forces, tearing apart the very fabric of reality. This was proposed in 2003 by Robert Caldwell, Mark Kamiankowski, and Nevin Weinberg. It depends on the nature of dark energy. If dark energy is a phantom energy with a particular kind of negative pressure, its density will increase as the universe expands. This creates a runaway feedback loop. More expansion leads to more phantom energy, which leads to even faster expansion. The timeline of the Big Rip is brutal and precise. Billions of years from now, the accelerating expansion would first overcome gravity on the largest scales. About 60 million years before the end, the Milky Way galaxy would be torn apart as stars are flung into the void. 3 months before the end, the gravitational pull holding the solar system together would fail. The Earth would be ripped away from the sun. In the final minutes, the Earth itself would explode. And in the last 10 raised to the power of 19 seconds, atoms would be broken apart. Finally, at the moment of the Big Rip, the expansion rate would become infinite. Space-time itself would tear, and the concept of distance would lose all meaning. Every point would become infinitely far from every other point. This is just one possible fate for the universe. It depends on the equation of state parameter for dark energy, denoted by the letter W. If W is exactly 1, we get a steady expansion, the big freeze. If W is greater than 1, the expansion might even reverse the big crunch. But if WAP is less than 1, we get phantom energy and the Big Rip. Current measurements from projects like the Dark Energy Survey are trying to pin down the value of WAP. The data so far is very close to 1, making the big freeze the most likely scenario. But the measurements have uncertainties. The possibility that our space-time is destined not to freeze or crunch, but to be violently ripped into infinite pieces remains on the table. Number 14, the loop in time. General relativity allows for the possibility of space-time geometries that contain closed time-like curves, CTCs. A CTC is a path through space-time that an object could follow to return to its own past. It is, in essence, a time machine. The existence of CTCs would warp the fabric of space-time so severely that the distinction between past, present, and future breaks down. The first person to find a solution to Einstein's equations that contain CTCs was Kurt Gödel in 1949. Gödel was a logician and a close friend of Einstein's at Princeton. He discovered that if the entire universe were rotating, time travel to the past would be possible. An object could travel in a large enough circle and arrive back at its starting point before it left. Our universe does not appear to be rotating in this way, so Gödel's model doesn't describe our reality, but it showed that time travel was not forbidden by the laws of relativity. Other, more plausible seeming ways to create CTCs have since been proposed. For example, a wormhole, if its mouths were manipulated correctly, could be turned into a time machine. One mouth could be taken on a high-speed journey and then brought back. Due to time dilation, less time would have passed for the moving mouth. Someone entering the stationary mouth could then emerge from the moving mouth in the past. Another idea involves infinitely long, massive spinning cylinders, a concept known as a Tipler cylinder. The existence of CTCs leads to famous paradoxes. The most well-known is the grandfather paradox. What if you travel to the past and prevent your own grandparents from meeting? Then you would never have been born to go back in time in the first place. This logical contradiction has led physicists to propose chronology protection principles. Stephen Hawking proposed a chronology protection conjecture, suggesting that the laws of physics conspire to prevent CTCs from forming. For instance, creating a wormhole time machine might require negative energy, which may be impossible to collect in sufficient quantities. Or, the quantum vacuum fluctuations at the entrance to a time machine could become infinitely strong, creating a wall of energy that destroys the machine before it can be used. Space-time itself might have a built-in defense mechanism against such paradoxes. Number 13, surfing a space-time wave. Traveling faster than the speed of light is impossible, according to special relativity. An object with mass would require infinite energy to reach light speed. But what if you could move space-time itself, instead of moving through space-time? This is the idea behind the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994. It is a theoretical way to achieve faster than light travel that does not violate relativity. The Alcubierre drive works by creating a warp bubble of flat, undisturbed space-time around a spaceship. In front of the bubble, space-time is contracted. Behind the bubble, space-time is expanded. The ship itself doesn't move at all within its local bubble. It's the bubble that moves, carrying the ship with it. It's like a person standing on a rug and someone else pulls the rug across the floor. The person isn't walking, but they are moving relative to the room. Because the ship isn't moving locally, it doesn't experience any of the strange effects of relativity, like time dilation or mass increase. From the perspective of someone on board, the journey could be instantaneous. The problem is the energy requirements. You know, to create this distortion in space-time, the drive would need a ring of exotic matter with negative energy density. Negative energy is a real concept in quantum physics. The Casimir effect is one example, but creating and controlling enough of it to power a warp drive is currently far beyond our capabilities. The initial calculations by Alcubierre required an amount of negative energy equivalent to the mass of the entire observable universe. Later refinements by Harold Soni, White, and others at NASA have brought the requirements down significantly, perhaps to the mass of a large planet like Jupiter. But it's still an astronomical amount. There are other problems too. The front of the warp bubble would act like a cosmic snowplow, accumulating interstellar particles and radiation. When the drive is turned off, all this accumulated energy would be released in a massive destructive burst of gamma rays, incinerating anything at the destination. Also, someone inside the bubble would be causally disconnected from the outside. They could not steer the ship or decide when to stop. The journey would have to be pre-programmed. The Alcubierre drive shows how space-time can be manipulated in theory, but the practical hurdles suggest it will remain a science fiction concept for the foreseeable future. Number 12, walls between realities. In the very early universe, as it cooled down after the Big Bang, the fundamental fields that govern physics may have frozen into different states and different regions of space. The boundaries between these regions would be two-dimensional defects in space-time called domain walls. A domain wall would be a membrane of immense energy, a wall separating two different vacuums with different physical laws. You can think of it like water freezing into ice. As the water cools, ice crystals start to form at different points and grow outward. The crystals have different orientations. Where two growing crystals meet, they form a boundary, a defect in the crystal structure. In the same way as the universe cooled, different regions may have settled into a ground state independently. Where these regions met, a domain wall would form. A single, stable domain wall stretching across the observable universe would be a cosmological disaster. Its gravitational effects would be enormous. It would dominate the expansion of the universe and would produce anisotropies or variations in the cosmic microwave background that we do not see. The fact that we have a relatively smooth and uniform universe is strong evidence that no such stable domain walls exist within our observable horizon. However, that doesn't mean they couldn't have formed and then been destroyed. The theory of cosmic inflation, the rapid expansion of the early universe, would have stretched any domain walls that formed before it to a colossal size, pushing them far beyond our observable horizon. So they could exist, but we would never see one. Another possibility is that the network of walls was unstable and collapsed and decayed early on, leaving behind only gravitational waves as a signature. Some more exotic theories propose that our universe itself could be a domain wall. In this scenario, we live on a three-dimensional wall embedded in a higher dimensional space. This connects to the brain world ideas. The existence of domain walls would mean that space-time is not a single monolithic fabric. It could be a patchwork quilt of different regions with different fundamental properties, with reality itself changing as you cross from one patch to another. Number 11, the universe's cracks. Cosmic strings are not made of matter. They are one-dimensional defects in the fabric of space-time itself. They are leftovers from the phase transitions of the early universe, similar to domain walls, but in the form of incredibly thin, incredibly dense lines of energy. A cosmic string would have no thickness in 2 dimensions. It would be a line of pure primordial energy stretching across vast cosmic distances. They could be closed loops or extend across the entire observable universe. These strings would be unimaginably dense. A string just 1.6 kilometers long would have a mass equal to that of the Earth. This immense mass and tension would warp space-time around it in a very peculiar way. Space-time around a cosmic string would not be curved like it is around a star. It would be flat, but with a piece missing. It would be shaped like a cone. This conical geometry would have strange effects. You know, if you were to travel in a circle around a cosmic string, you would find that you have to travel less than 360 degrees to get back to your starting point. The string creates a kind of shortcut. This would also lead to a unique form of gravitational lensing. A cosmic string situated between us and a distant galaxy would not produce multiple distorted images of the galaxy as a massive cluster would. Instead, it would produce 2 identical, undistorted images. Finding such a pair of images would be a smoking gun for the existence of a cosmic string. Astronomers have been searching for these signatures for years, but none have been found yet. Moving or vibrating cosmic strings would also be a powerful source of gravitational waves. The Laser Interferometer Space Antenna LISA, a future space-based gravitational wave observatory, might be able to detect the faint background hum of gravitational waves produced by a network of cosmic strings left over from the early universe. If they exist, cosmic strings are fossil relics from the universe's first moments, titanic threads of energy that warp space-time in a way unlike anything else. Number 10. The Cosmic Fountain. A white hole is the theoretical time reversal of a black hole. While a black hole is a region of space-time that nothing can escape from, a white hole is a region that nothing can enter. Matter and light can only flow outwards from it. It is a source, a cosmic fountain that erupts matter and energy into the universe, but can never be entered from the outside. Mathematically, white holes are a valid solution to the equations of general relativity. The first full description of a black hole, the Schwarzschild solution, actually describes an eternal black hole that is connected to a white hole through a wormhole, known as an Einstein-Rosen bridge. In this picture, anything that falls into the black hole could, in theory, emerge from the white hole somewhere else in space-time, or even in another universe. However, most physicists believe that white holes are purely mathematical curiosities and do not exist in reality. The process of forming a black hole through the collapse of a massive star does not seem to have a corresponding time-reversed process that would form a white hole. A white hole would require matter to spontaneously emerge from a singularity, which would violate the second law of thermodynamics, the law that states that entropy disorder in a closed system must always increase. A white hole would be a system of decreasing entropy. Despite this, some physicists have explored ideas where white holes might play a role in the cosmos. One speculative idea proposed by Carlo Rovelli and Hal Haggard is that white holes could be the end stage of black hole evaporation. According to Stephen Hawking, black holes slowly lose mass over time through Hawking radiation. One possibility is that when a black hole becomes very small, quantum gravity effects cause it to bounce and transition into a white hole. This tiny white hole would then release all the remaining information that had fallen into the black hole in its final moments. Another fringe idea is that the Big Bang itself was a white hole. In this model, our entire universe is the material that erupted from a single supermassive white hole. This is not a mainstream view, but it shows how the strange geometry of a white hole, a place where space-time itself flows outward, continues to provoke new ideas about the origins of our cosmos. Number 9, the shortcut through everything. A wormhole, or an Einstein-Rosen bridge, is a hypothetical tunnel through spacetime that could connect two very distant points, creating a shortcut. It's a way to bend spacetime so severely that it creates a new topological connection. You could enter a wormhole in the Milky Way galaxy and emerge in the Andromeda galaxy moments later, having traveled a few meters through the wormhole's throat instead of 2.5 million light years through normal space. The idea comes from the mathematics of general relativity. The same equations that describe black holes also allow for these tunnel-like structures. The original Einstein-Rosen bridge, however, was not traversable. It was dynamic, pinching off so quickly that not even a beam of light would have time to pass through it. To create a stable, traversable wormhole, you would need to prop its throat open. This is where the problems begin. Propping a wormhole open requires, once again, a form of exotic matter with negative energy density. This matter would have to possess a strong negative pressure, essentially acting as a kind of anti-gravity to push the walls of the wormhole's throat apart and prevent it from collapsing into a singularity. As with the warp drive, while negative energy is known to exist in small amounts in quantum phenomena, there is no known way to produce and control it on the scale needed to sustain a macroscopic wormhole. If one could be created, the implications would be staggering. A wormhole not only connects 2 points in space, but also 2 points in time. As discussed with closed time-like curves, manipulating one mouth of a wormhole could turn it into a time machine, leading to all sorts of paradoxes. Despite the theoretical hurdles, the concept of wormholes remains a serious topic of study. They represent a fundamental question about the nature of spacetime. Is the topology of spacetime fixed, or can it be changed? If wormholes are possible, even just at the microscopic quantum foam level, it would mean that the fabric of our universe is far more interconnected and complex than it appears. It could be riddled with tiny fleeting tunnels to other places and other times. Number 8. The densest matter imaginable. A neutron star is the collapsed core of a massive star that has gone supernova. It is one of the densest objects in the universe. A typical neutron star has a mass about 1.4 times that of our Sun, but it is squeezed into a sphere only about 20 kilometers in diameter. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth. This extreme density creates a gravitational field at its surface that is 200 billion times stronger than Earth's, warping space-time in its immediate vicinity. The matter inside a neutron star is unlike anything on Earth. The immense pressure crushes protons and electrons together to form neutrons, creating a substance called neutronium. The star is so dense that it is essentially a single gigantic atomic nucleus. Its properties are governed by the strong nuclear force and the laws of quantum mechanics. This intense gravity has measurable effects. Light leaving the surface of a neutron star is severely gravitationally redshifted, meaning its wavelength is stretched and it loses energy as it climbs out of the star's deep gravity well. The warping of spacetime is so pronounced that you can see more than half of the star's surface at once. The light rays from the back of the star would be bent around to the front. When two neutron stars orbit each other, they create powerful ripples in space-time psi-gravitational waves. As they radiate this energy, they spiral closer together. On August 17, 2017, the LIGO and Virgo observatories detected the gravitational waves from such a merger, an event named GW1. Seconds later, gamma-ray telescopes detected a burst of light from the same patch of sky. And telescopes all over the world turned to look. They saw the explosion, a kilonova, and for the first time were able to study the electromagnetic light from a gravitational wave event. This event confirmed a long-held theory that the collision of neutron stars is one of the primary places in the universe where heavy elements like gold, platinum, and uranium are forged. The gold in your jewelry was likely created in the cataclysmic merger of two neutron stars, an event that warped space-time so violently that we could feel the tremor 100 million light-years away. Number 7. The point of no return. A black hole is not an object. It is a region of space-time where gravity is so strong that nothing, not even light, can escape. The boundary of this region is called the event horizon. It is not a physical surface. It is a one-way membrane in the fabric of spacetime. Crossing the event horizon is an irreversible act. Once you are inside, all possible paths lead to the center, to the singularity. The size of the event horizon is determined by the black hole's mass. This is called the Schwarzschild radius. For a black hole with the mass of our sun, the event horizon would have a radius of about 3 kilometers. For the supermassive black hole at the center of our galaxy, Sagittarius A, which has a mass of about 4 million suns, the radius is about 12 million kilometers. The experience of crossing an event horizon would be surprisingly gentle for a large enough black hole. For a supermassive black hole, the tidal forces at the horizon are weak. You wouldn't feel anything special at the moment of crossing, but your fate would be sealed. From the perspective of a distant observer, you would appear to slow down as you approached the horizon, becoming redder and dimmer due to gravitational time dilation and redshift. They would never actually see you cross. Your image would seem to freeze at the horizon, fading away over an infinite amount of time. From your perspective, however, you would cross the horizon in a finite amount of time and continue your fall toward the center. Inside the event horizon, space-time is warped to an extreme degree. The roles of space and time are swapped. The direction toward the singularity, which was a direction in space, becomes a direction in time in the future. Just as you cannot avoid moving into your future, an object inside a black hole cannot avoid moving toward the singularity. It is an inevitability written into the geometry of space-time itself. The event horizon is the ultimate boundary, a place where the forward march of time becomes an inexorable fall into a point of infinite density. Number 6, the universe's endless stretch. Space-time is not a static stage on which events unfold. The fabric of space-time itself is dynamic. And it is expanding. This is not like an explosion where galaxies are flying away from a central point through space. Instead, the space between galaxies is stretching, carrying the galaxies along with it. A common analogy is to imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move farther apart from each other, but they are not moving on the surface. The surface itself is expanding. This expansion was first observed by Edwin Hubble in the 1920s. He noticed that the farther away a galaxy is, the faster it is moving away from us. This relationship is known as Hubble's law. This expansion of space-time is a core prediction of general relativity when applied to the universe as a whole. And Einstein himself initially introduced a cosmological constant into his equations to force a static universe, which he later called his biggest blunder after Hubble's discovery. For billions of years, this expansion was thought to be slowing down due to the gravitational pull of all the matter in the universe. But in 1998, 2 teams of astronomers studying distant supernovae made a shocking discovery. The expansion is not slowing down, it is accelerating. Something is pushing space-time apart, overcoming the pull of gravity. This mysterious something was named dark energy. Dark energy now appears to make up about 68% of the energy density of the universe. We don't know what it is. It could be the cosmological constant that Einstein first proposed, an intrinsic energy of the vacuum of space itself. Or it could be something else entirely, a new field or force. This accelerating expansion has a strange consequence. There's a cosmic horizon. Galaxies beyond a certain distance are receding from us faster than the speed of light. This doesn't violate relativity because it's space itself that is expanding, not the galaxies moving through space. But it means that the light from those galaxies will never reach us. They are effectively cut off from our observable universe. As the expansion continues to accelerate, more and more galaxies will cross this horizon, and the night sky of the distant future will be a much emptier, darker place. The very fabric of reality is stretching out from under us, carrying the universe away. Number 5, the golden collision. The merger of 2 neutron stars is one of the most violent events in the universe. It is a collision that involves extreme gravity, extreme density, and extreme physics. For a brief moment, the collision creates an object that is more massive than the most massive stable neutron star. The outcome can be one of two things. It either collapses immediately to form a black hole, or it forms a temporary hypermassive neutron star that is supported by its rapid rotation for a few milliseconds before it too collapses. In either case, the event sends a shock wave through spacetime. The gravitational waves from this process, like the one detected in 2017, carry detailed information about what happens during the merger. The signal allows scientists to measure the tidal deformability of the neutron stars. As they get closer, the immense tidal forces of each star stretch and deform the other. The extent of this deformation tells us about the properties of the matter inside the neutron star equation of state, which describes how pressure and density are related in such extreme conditions. This is physics that cannot be replicated in any laboratory on Earth. The merger also ejects a significant amount of neutron-rich material into space at high speeds. This material then undergoes a process of rapid neutron capture, or the process, where atomic nuclei quickly absorb free neutrons to build up to very heavy elements. The subsequent radioactive decay of these unstable new elements powers a thermal glow called a kilonova. The observation of the kilonova associated with GW17817 was a landmark moment in astrophysics. By analyzing the spectrum of the light from this event, astronomers found clear signatures of heavy elements like strontium and evidence for the production of gold and platinum. The analysis suggested that this single merger created somewhere between 3 and 16 times the mass of the Earth in heavy R-process elements. This confirmed that these mergers are a major, if not the primary, source of the heaviest elements in the universe. The space-time warp from these collisions is the cosmic forge that creates the precious metals we find on Earth. Number 4, the chirp heard round the universe. The collision of two black holes is a purely gravitational event. There is no matter involved to create light or explosions. There is only the warping of space-time as two black holes spiral into each other. They churn space-time like a blender, sending out a continuous train of gravitational waves. These waves carry away orbital energy, causing the black holes to spiral closer and faster. In the final fraction of a second, this process becomes a runaway catastrophe. The black holes are moving at a significant fraction of the speed of light. The gravitational waves they emit become stronger and higher in frequency. This is the chirp that LIGO detected. The frequency of the wave is directly related to the orbital speed of the black holes. The amplitude of the wave is related to their masses. By analyzing the precise shape of this chirp signal, scientists can deduce the masses of the two original black holes, the mass of the final black hole, and how much energy was radiated away. The first detection, GW15914, was a perfect example. The signal showed two black holes of 29 and 36 solar masses merging to form a single black hole of 62 solar masses. The missing 3 solar masses were converted directly into gravitational wave energy, according to E = mc squared. This was an amount of energy equivalent to detonating millions of trillions of 1 megaton bombs. For a fraction of a second, the power radiated by this single black hole merger was more than 50 times greater than the power radiated as light by all the stars in the observable universe combined. This event was the first direct observation of black holes. It was the first direct observation of a binary black hole merger, and it was the first time we saw space-time being pushed to its limits. The final merged black hole is not perfectly spherical at first. It is a distorted, quivering blob of space-time. It settles down to a stable state by radiating away its imperfections as a final burst of gravitational waves, a process called ring-down. This ring-down is like the sound of a bell being struck. By listening to this cosmic bell, we are directly probing the nature of space-time in the most extreme environment imaginable. Number 3, the cosmic twister. When a massive object spins, it doesn't just curve space-time, it drags space-time around with it. This effect is called frame dragging, or the Lenz-Thirring effect. It was predicted by Austrian physicists Josef Lenz and Hans Thirring in 1918 using Einstein's theory of general relativity. The effect is incredibly small and difficult to measure. Near a spinning object, the very fabric of space is twisted into a vortex. Think of a bowling ball spinning in a tub of honey. The honey right next to the ball will be dragged around with it, and the honey farther away will be dragged less. Frame dragging is the space-time equivalent of this. A gyroscope placed in orbit around a spinning body will not point in a fixed direction. The twisted space-time will exert a tiny torque on the gyroscope, causing its axis of rotation to precess or wobble over time. This effect is most pronounced around rapidly rotating, massive objects like black holes and neutron stars. Around a spinning black hole, there is a region outside the event horizon called the ergosphere. Within the ergosphere, the dragging of spacetime is so intense that nothing can stand still. An object inside the ergosphere must move in the direction of the black hole's rotation, even if it fires its rockets in the opposite direction. Space itself is moving faster than light relative to a distant observer. The only way to escape the ergosphere is to be thrown out by stealing some of the black hole's rotational energy, a process known as the Penrose process. Frame dragging has been measured here in our own solar system. A dedicated NASA mission called Gravity Probe B was launched in 2004 to measure this effect from the Earth's rotation. The experiment involved 4 of the most perfect spheres ever created by humans, coated in a superconductor and cooled to near absolute zero, acting as ultra-precise gyroscopes. After analyzing years of data and accounting for numerous sources of error, the science team announced in 2011 that they had measured the frame dragging effect. The gyroscope's axes had been dragged by a minuscule 39 milliarseconds over the course of a year. It was a tiny shift, but it matched the prediction of general relativity perfectly. It was direct proof that our own planet twists the fabric of space-time as it spins. Number 2, Earth's subtle twist. Every object with mass warps spacetime, including the Earth. The effect is small, but it is not zero, and it has a direct impact on our daily lives. The most important consequence is gravitational time dilation. According to general relativity, time runs slower in a stronger gravitational field. A clock at sea level will tick slightly slower than a clock on top of a mountain. A clock on the surface of the Earth will tick slower than a clock in orbit high above the Earth. This is not a theoretical curiosity, it is a crucial correction for the Global Positioning System GPS. The GPS network consists of a constellation of satellites orbiting the Earth at an altitude of about 20,200 kilometers. Each satellite carries an extremely precise atomic clock. There are 2 relativistic effects that must be accounted for. First, due to special relativity, the clocks on the moving satellites tick slower than stationary clocks on the ground. This effect amounts to about 7 microseconds per day. But the effect of general relativity is much larger and works in the opposite direction. The satellites are in a weaker gravitational field than we are on the surface, so their clocks tick faster. This effect amounts to about 45 microseconds per day. The net result is that the clocks on GPS satellites run faster than clocks on the ground by about 38 microseconds, 45 minus 7 every day. 38 microseconds might not sound like much, but GPS works by precisely timing signals traveling at the speed of light. If this relativistic correction were not made, the system would be useless. An error of 38 microseconds would translate into a positional error of about 10 kilometers. This error would accumulate every single day. Within a few minutes, the GPS in your phone or car would tell you that you are miles away from your actual location. So every time you use GPS to navigate, you are relying on Einstein's theory of general relativity. You are using a system that is engineered to account for the fact that our planet's mass warps space-time and alters the flow of time itself. The subtle curve in space-time created by the Earth is a fundamental part of the technology that powers modern navigation. Number 1. The sun's simple dent. The first experimental test of general relativity involved the simplest and most familiar warping of spacetime, the dent created by our own sun. Isaac Newton's theory of gravity described gravity as a force between objects. In Newton's view, light, being massless, should not be affected by gravity. Einstein's theory was different. It said that gravity is the curvature of space-time caused by mass and energy. A massive object like the sun creates a dip in the fabric of space-time. Anything traveling through that space-time, including light, must follow the curves. This led to a testable prediction. Starlight passing near the sun should be deflected by the sun's gravity. The position of a star seen near the edge of the sun should appear to be shifted slightly from its true position. The amount of this deflection predicted by Einstein was about 1.75 arcseconds, a tiny angle. Crucially, this was exactly twice the deflection that would be predicted if you tried to apply Newton's laws to light, treating it as a particle. The only time you can see stars near the sun is during a total solar eclipse, when the moon blocks the sun's bright disk. In 1919, 2 expeditions were organized by the British astronomer Arthur Eddington to observe a solar eclipse. One team went to Sobral, Brazil, and the other, led by Eddington himself, went to the island of Principe off the coast of West Africa. They took photographs of the stars around the sun during the eclipse. They then compared these photographs to pictures of the same star field taken at night months earlier. The analysis was difficult, but the results were clear. The positions of the stars had shifted, and the amount of the shift was consistent with the prediction of general relativity, not the Newtonian prediction. The announcement of the results in November 1919 made Einstein an international celebrity overnight. It was the first proof that gravity is not a force, but a feature of the geometry of the universe. The simple dent in space-time made by the sun reshaped our understanding of reality. It showed that the very stage on which our lives play out is not fixed and absolute, but is a flexible, dynamic entity that is bent and warped by every object within it.